Okay, let's continue. In the last class, essentially it was a basic recap on the MOSFET and the regions of operation. So just to summarize the discussion, so you saw that a MOSFET, irrespective of whether it's biased in saturation or in triode region, with respect to small signals, it behaves like a voltage controlled current source with an output resistance. And but still you prefer to bias it in saturation because, as we saw, even though in linear region the transconductance was similar, the output resistance was significantly small, so the intrinsic gain is much smaller than 1. And this also made sense because from your two-port network point of view, to get power amplification, if you recollect, you had to bias your, or you need to have an output characteristics like this, where the slope is really small. So it makes sense that you operate your transistors in a region where the current saturates, or it varies very small with respect to VDS. Right? And we also saw that for VGS less than the threshold voltage, in practice you still have current flow, and that is exponentially related to VGS. And even here, after a particular value of VDS, the current kind of saturates. So even here you have saturation. So you could bias your transistor in weak inversion in the saturation region to get good gain. And in fact, we saw that for a given drain current, which had a better transconductance in weak inversion or in strong inversion? It was in weak inversion where you had a higher transconductance for a given current, and we characterized it using this ratio GM by ID, and that kind of says the power efficiency, that is how much power I should consume in a transistor to get a particular GM. But even though the GM you can get here is higher, what was the downside in weak inversion? The intrinsic gain is similar. The speed, as I mentioned, it's this one, because the currents are going to be small, and to bias the transistor in weak inversion, your sizes will be really large. So capacitance increases, so together it reduces speed. So because of the speed reasons, so we'll mainly try to bias the transistor in saturation. When I say saturation, it is in strong inversion, okay? Because strictly speaking, saturation happens here also after this VDS. But in this course, we will just follow this notation that when I say saturation, it is in this region, and as and when required, we will draw comparison between these two. Okay. Yeah, but when you are concerned only about power, it's okay to bias in weak inversion. And as I mentioned, in electronic watches is when people try to do it, and that's where this all started. And then we also saw for PMOS we have similar. So let me just brush that up and continue. So PMOS is similar. The current flow just changes from, for NMOS it flows from drain to source. For PMOS it is flipped. So the way I see it is all the potential differences kind of reverse. So gate to source becomes source to gate and so on, right? Can you close the door? And this is the current equation. So here once again, if I make small changes to source to gate voltage, the drain current changes. Once again, to model this, you do the same thing. This is, let us say, gate, drain and source. So here in response to a source to gate voltage, a current flows from source to drain. So you have, strictly speaking, the model is this, where this is GM, the SG, but I can also do the following. I can change the direction of the current and then call that this is GM times VGS. Okay. And again, you have the dependence of drain to source voltage is captured with a resistor R. So with respect to small signals, there is virtually no difference in using an NMOS transistor or a PMOS transistor. Okay. And not just that, it doesn't matter where the transistor is biased in. It could be in triode region, weak inversion, strong inversion, any different region. At the end of a day, NMOS transistor or a PMOS transistor in any region, it is a voltage controlled what source? Current source with an output resistance R0. The only difference will be the value of this transconductance and the output resistance. That's it. And for that matter, any transistor starting from vacuum tubes, bipolar transistors, MOSFET, FinFET, gate all around FET, everything, they will all be voltage controlled current source, because what was the motivation for inventing transistor? Why did they want to make transistor? They want to make switches, they want to replace mechanical switches, and that's where it started. And as you know, switch is a 3-terminal element where the current flowing between 2 terminals depends on, what does it depend on? The voltage applied at this terminal. So in fact here you see that the current in between 2 terminals depends on a voltage. So what kind of control source you can think of it as? So again a voltage controlled current source loosely. Okay. So that's what we will be doing in the throughout the course. We'll understand what happens when you have voltage controlled current source. So whatever you learned here, it's kind of universal. The only thing changed with different transistors evolution is the IV relation, the value of Gm, R0, etc. Okay. And one last point about MOSFET. So let's say you have an NMOS transistor. It turns out a MOSFET is symmetrical by construction. That is, if you see a transistor, you might not be able to differentiate which is drain and which is source, right? So then in circuits, how do you make the distinction? I mean, in NMOS transistor, how do you decide which is the drain terminal or which is the source terminal? Depending on? I mean, okay, not okay, partially right, but the idea is, see, in a MOSFET, the NMOS transistor, the current is flowing from drain to source. So the point is, the terminal with the higher potential will be called drain. That's all. Okay. For example, if I call it, let us say terminals 1 and 2, and let's say I connect V1 and V2. Let's say I change these. As long as V1 is greater than V2, the terminal 1 will be drain, terminal 2 will be source, and this is the current flow. Again, it's fundamental, current flows from the higher potential to a lower potential. That's it. Similarly, if the scenario reverses, what happens now? I mean, yeah, terminal 2 becomes drain. Okay, this becomes drain, this becomes source. So current again flows from higher to lower potential. So the names drains and source, they're all placeholders. It is like, you know, number 1 ODI team, number 2 ODI team. It is not always Australia's number 1, India's number 2. Next year it will change. Something like that, right? So terminal with the higher potential is drain for NMOS. Source is lower potential is source. So depending on the operations or what's happening in the circuit, their roles can flip. So same thing will happen for PMOS. In a PMOS, the terminal with the higher potential is source. Okay. Because in a PMOS, the current flow is from source to drain. So that higher potential, the terminal with the higher potential is called as source. That's all. Otherwise, there is no big distinction between these two terms. Great. So now you know that a transistor essentially has a current flowing between drain and source, and this current majorly depends on what voltage? The current in a transistor mainly depends on what voltage? Gate to source voltage. So in a way I will say that gate to source voltage is the cause. So that can be thought of as the input, and the current flowing between drain and source is the effect. That can be considered as the output. So now you have combinations to play with. You can apply the input at the gate, tap the output from the drain, input at the gate, output at the source, input at the source, output at the drain, and this gives rise to the 3 basic configurations that you would have already learned. Let's quickly brush them up and move on. Let's start with the first case. I apply input at the gate, take the output at the drain. So what kind of configuration is this called as? Common source, yeah. This is the common source. So let's say I have something like this. So I apply a small signal V in. Again, remember that in practice I cannot directly apply the small signal voltage to amplify. What should I add in along with this? The bias voltage. Because again, remember the transistor has to be biased in saturation. Again, the analogy I give for biasing is this, right? I mean, let's say you want to, ask your parents to buy you something or get a favor from your parents. Will you ask them whether if they are in a good mood or in a bad mood? Yeah, you won't ask them if they are already shouting at someone and like in a bad mood. At least you will try to make sure you go home, all do household work and praise them saying you are the best father, best mother, best parents in the world, blah blah blah, and make sure you butter them up nicely and then say, buy me this. Same thing you do here. You want to get maximum gain from a transistor. You make sure the transistor is happy by giving a proper bias voltage, and then you kind of ask the gain from it. So yeah, maybe to avoid confusion, I'll just draw the incremental equivalent where for small signals the supply is short, right? So that there is no confusion. I assume that the biasing is taken care of. So if I have this, what is the small signal output here? If I make a change in the gate voltage by Vi, what is the corresponding change seen at the drain side? Minus Gm times Rd. Yeah, again, remember for small signals I can consider the MOSFET to be a voltage controlled current source. The value is Gm VGS. Here VGS is what? Vi, that's it. And of course if you include R0, that's going to come in parallel. So what is the current flowing in this direction upwards? Minus GMVI. So that flows through a parallel combination of RD and R0. That's what you get. So this is one configuration where you can get sufficiently good gain. So that's about common source. So now let's look at the second case, input at the gate, output at the source. If I apply input at the gate, output at the source, what terminal is common? Drain. So obviously you name it as common drain. And let's say I have something like this. I bias it with the current source, let us say, for example. Here maybe I'll show it with the biasing. Some bias voltage plus small signal. And again, to start with, let's ignore R0. Again, this is something you try to do, because whenever you have a new circuit or trying to analyze something, first you get rid of all non-idealities so that you get a feel for what's happening in the circuit. And then once you get a qualitative feel, you can include all non-idealities and see. So here, if I ignore the effect of R0, then if I make changes at the gate voltage if the gate voltage is changed by Vi, how much will be the change at the source voltage? Yeah, why same? Sorry, I can't hear you. Amplify it further now.
Because the I0 current source will be open in small signal model.
Yeah, I mean that's one way to look at it. Again, you can draw the small signal and do it, but yeah, I guess everyone is kind of hinting at the same thing. The idea is this, right? See, here, what is the current flowing in the transistor? Total current in the transistor. Will it change if I change the gate voltage? Why? The current source is kind of sitting there and making sure the current is I0. If the current is constant and equal to I0, what can you say about the gate to source voltage? Will it change? Current only depends on VGS because I've ignored R0. So which means if the current is constant, gate to source voltage is constant. So if the gate voltage changes by something, source voltage will faithfully track it. Nothing will happen. So Vout is exactly. Yeah. Is that fine? Okay. I mean, you can also get this by drawing the small signal, but that's something you would have done in your first analog circuits course. But now let's try to get more qualitative feel for what's happening. So yeah, you see that the gain is now 1. So what is the point of having a gain of 1? Yeah, sure, you guys know its main purpose is to be used as a voltage buffer. And voltage buffer is what kind of a control source? It is sensing a voltage and reproducing another voltage. So it is a voltage control voltage source. So again, just so that everyone is on the same page, you need a buffer because of the following reason. So you have an input voltage Vi. It could have a series resistance Rs. So if you try to connect it to some other element, let's say it has an effective resistance RL. If I go and directly connect it, what will happen? Will I get the entire Vi across RL? Only a fraction of it will be delivered to RL. So that's where you take help of a voltage buffer. So the idea is this, you have this. Now you connect a buffer here. What is the input resistance of an ideal buffer? Infinite because it wants to make sure the entire voltage drops across the input of the voltage buffer. So it has an infinite input impedance, and then it kind of copies this voltage and feeds it to the load R. And ideally, what is the output resistance of a voltage buffer? 0. It's supposed to behave like an ideal voltage source here, but in practice there can be a small output resistance. As long as it is sufficiently small, it's okay. Okay, again, small, large, they are all relative terms. So at least in this case, can you tell me R out should be smaller than what value, so that doing this is better than this? Smaller than? Not RL. Why RS? There are only two resistors, so one of them should be the answer, obviously. Well, I mean, think about it. If let us say R out is much larger than RS, the fraction of voltage appearing here will be higher than what appears here, right? So obviously R out should be at least smaller than RS. Else, if R out is greater than RS, there is no point in doing this. I could as well have done this, right? So that's why if R out is smaller than RS, it is fine, and that's about it. So let's see what is the impedances here. What is the input resistance here? Infinite. Again, we are looking at the input resistance, so gate has only capacitance, so it's infinite. And what about the output resistance? Yeah, everyone remember, so but let's quickly do it. If you want to calculate an output resistance or resistance at some point, what do you do? Yeah, let's quickly draw that. If I apply, let's draw the incremental equivalent. So the drain is incrementally short, and then I have this fellow. To find the effective impedance at this node, what do I do to the gate? All the other sources are made 0. Voltage source, if you make it 0, it's a short, and as he mentioned, you try to apply a test voltage source and try to find the test current, or you can apply a test current source and find what is the test voltage developed. For LTI circuits, both are identical, nothing changes. So again, for small signals, you have the transistor behaving like a VCCS. What is the value of the current source? GM VGS. What is VGS here? Minus VT, which means I can flip the direction. So this is going to be GM times VT. Okay. So now you see that I have a voltage VT, a current GM times VT is drawn out of that node. So it's as though I have a resistance of how much? So as long as GM is sufficiently large, you have a small output resistance, which is what you want from an ideal, from a good voltage buffer. Okay. So now let's quickly repeat this with R naught considered. So let's say this is with R naught. So once again, to calculate what is the change seen at the source if the gate changes, you can resort to small signal and do it, but we will do something else here, and this is something we might do a lot of times in the course, and that is the following. For small signals, can you tell me if this is a linear network or a non-linear network? Linear network. If I have any linear network, this is a linear network, and let us say I'm defining something as the Vout. So if this is a linear network, with respect to these two terminals, how can I simplify this entire network as? Thevenin or Norton, either of them is fine, and we prefer Norton in generally. So let us say this is modeled as an effective current, Norton current, and the Thevenin or Norton resistance, and that's essentially the resistance looking into this port, and since we call it the output port, we'll call this the output resistance. So this is my Vout. Right? Now, how do you find the, let's say this is the network you have, okay. So let's say this is what you have, this is the same network, right? So if I were to find the Norton current, what would you do here?
Find the short circuit current.
Yeah, you try to short circuit the output. Again, I'll have to be more careful. This is the two terminals. So what do you do? If you short circuit the output like this, so the entire current here flows to the output. So you simply measure the short circuit current and that gives you the Norton current. So remember my V out. What is my V out here in terms of the current and resistance? It's confusing. I mean, what is V out here in this circuit? IN times R out. And the Norton current is essentially the short circuit current. Okay, that's all. This is fine. And let's say in this circuit or any circuit, I'll have short circuit current flowing because I have applied some voltage source here. And this is a linear network. How will the short circuit current be related to the voltage? It's a linear network, so the relation will also be linear. So I will say that this is some Gm times Vi times R. This is fine. So which means the ratio V out by Vi, I will call it the gain A, that is some Gm times R out, and this Gm is what we call as the short circuit transconductance. Okay. The idea is same. It's same. I mean, is essentially finding the Norton current. You short circuit the output, find the current, divided by the input excitation. That's assumed to be a voltage here. That gives you the short circuit Gm. And calculating this is typically easier because for finding the short circuit Gm, you are short circuiting the output. So circuit kind of simplifies. Right? That's the idea. So let's quickly do that for this case. Let me move it up. But this is principle fine. In any linear network, you can find the voltages like this. Right? Just model it as a Norton equivalent. Find the short circuit Gm, the output resistance. Take the product that gives the voltage gain. Again, that is assuming my input is voltage, output is voltage. So let's quickly do it for our circuit. So let's say I'm trying to find the short circuit Gm. I'm drawing the incremental equivalent of this. So the drain is shorted. I have the MOSFET, small signal Vi applied. What do I do to the output? I'm trying to find the short circuit Gm, so I'll have to short circuit the output. I'm short circuiting it, and I'm interested to find the short circuit current. And if I model the transistor, I'll have a current and R0. This okay? Now look at R0. R0 is connected between two grounds. So is it relevant or not relevant? It's connected across two grounds, so it's not playing any role in this picture. And what is the value of this current source? Gm times Vi. So what is the short circuit current now? Gm times Vi. Of course, now we can ask, even this current source is connected between two short circuits. But remember, it's a freaking current source. It doesn't matter. Whatever is connected across it, it will make sure that the current is constant. So the short circuit current is small Gm times Vi. So what is the short circuit Gm here? Small Gm. That is the operating point transconductance of this transistor is essentially your short circuit Gm of this entire circuit. Is that fine? So this is Gm. Let's do R out also. Again, I'll try to find R out here. So if I draw the incremental equivalent, I have drain to be shorted, gate to be shorted, and I'll apply a test voltage here. Fine. And if I draw the equivalent of the transistor, it is a voltage controlled current source and R out, sorry, and R0. Now look at R0. R0 is connected, one terminal is connected here and the other terminal is grounded. So I can essentially redraw it like this. I'll say that R0 is basically connected here. Fine. Both are same. Because drain is incrementally short, I can put it here also. So now tell me, what do you think is the output resistance? Yeah, remember when I didn't have R0, when I just had this, what was the output resistance here? 1 by Gm. Now it looks like R0 is put in parallel, so R out is 1 by Gm parallel. That's all. So now we can find the overall gain by taking the product of this capital Gm and R out. Again, you can do it and you'll find that this is Gm times R0 by Is this clear? Because this is something we might do quite often, because here the circuit is simpler. I mean, you could, without doing it, you can directly do small signal and do it. But for bigger circuits, you'll find that calculating short circuit GM is easier and R out is easier, rather than directly drawing the small signal equivalent of the entire circuit and trying to find what is V out. Okay, cool. So yeah, before we move, one point about this R out. So if I have this, what is the effective resistance here? R out? Yeah, 1 by Gm parallel R0. In practice, how can you approximate it as? Why? Yeah, why? I mean, at any point you should keep asking why, right? I mean, until you are able to answer why to multiple levels, you are not thorough. Yeah, I mean, why R0 is larger?
1 by lambda ID.
Yeah, again, remember that we this is biased in saturation. The drain current, very small. I mean, I will say the dependence on drain current on VDS is very minimal. So R0 is large. So that's why R0 is, Gm R0 is typically greater than 1. So R0 is much greater than 1 by Gm. So it follows. So again, now remember that even if this transistor is biased in linear region, the looking in resistance is still this 1 by Gm parallel R0. The only thing that changes is values of Gm and R0. Okay. Great. Yeah. So one point is the looking in resistance into the source, it is not always approximately 1 by Gm. It actually depends on what is the resistance connected at the drain side. So you take this as an exercise and calculate what is the resistance looking here, including R0. Okay. So please take it as an exercise and work out using small signal. Let's say you have an RD and you find what is R out here. You will find that this output resistance indeed depends on RD. But of course, without doing the exact calculation, let's see this, right? Let's take some extreme cases of RD and see if my claim is valid. My claim is the resistance here depends on RD. So let's take some cases. Here, what is the value of RD? RD is 0. So one thing we know for sure is if RD is 0, the impedance is 1 by Gm. So what is other value of RD I can take? Infinite. Let's do that. If RD is infinity, this is essentially open. Or in the full picture, it's as though I have a current source. Small signal, it is open. It's as though I have a current source. So in small signals, it is open. So if I now try to calculate the resistance here, gate is incrementally short, and I apply a test voltage here and try to find the test current. So now, oops, the same thing comes. Oops. Current source and R0, and remember drain side is completely open. Now what can you say about this current IT? 0. Why? So? No current can flow. I mean, there is a loop here, but why should not any current flow here? there are two statements, right? So these two are not related.
The current can't flow out also because it's open in the top.
As he's saying, if yeah, what is the current here? Why 0? It's an open circuit, no path as you were saying, so this is 0. So what can you say about these two currents? They will be same. So I test is okay. But you have a current source here, right? What will happen to this current? Yeah, the only path it has is to essentially circulate with an R. So this current will not flow here or here, it will just circulate within itself. Remember, current requires a closed path for it to flow, right? So only if you have another path, something to ground, only then this current can flow out and come like this. Okay. So since I have broken it here, no current flows. Yeah, so if I test is 0, what is R out? Infinite. So if you see, I mean, now you see if RD is infinity, R out is actually infinity. So now tell me, I mean, you do this calculation, but without doing the calculation, can you tell me when can I say R out to be approximately 1 by Gm? For smaller values of RD or for larger values of RD? Right? So that much is at least clear from our discussion. I will say R out is approximately 1 by Gm. For small values of RD, again RD, I mean small, large, they are all relative terms. Here the comparison is with respect to R naught. So which means now tell me if R naught tends to infinity, or if I don't consider the effect of R naught, what is the output resistance? Huh? Why 1 by Gm? Yeah, he's saying that, I mean, the idea is if R naught is infinity, as long as I have a finite RD, it's going to be smaller than this. So then I can safely say that it is 1 by Gm. Sorry. Okay. This is something to remember. If the drain resistance is much smaller in comparison to the R naught of the transistor, is when the resistance looking into the source is 1 by Gm. The second point is essentially an extension of the first. Okay, clear? Great. So okay, one more extension of common drain. Now let us say, again I'll draw the incremental equivalent alone. Instead of biasing with the current source, let us say I bias here with the resistance Rs. Right. Let's quickly see what will be V out here. And again, first let's ignore R naught. So this again, let's try to quickly calculate using short circuit Gm and R out. So if I short circuit the output, what is the short circuit current flowing? Gm times Vi, right? Remember, source is incrementally short. I mean, if I short circuit this, source is incrementally short. VGS is, what is VGS in this case? Vi. So the current flowing is Gm times Vi. So what is the short circuit Gm? Gm of the transistor. And what is the output resistance? Yeah, I've ignored R naught essentially. So looking up it is 1 by Gm. But what is the resistance looking down? I mean, I have 1 by Gm here, Rs here. Both are in parallel. So R out is Rs parallel with 1 by Gm. So if I find V out by Vi, I'll call it A. So that will be Gm times this. If you simplify, you'll get Gm Rs by 1 plus Gm. So at least now you see hopefully the value of this. By inspection you can quickly see what is the gain. Right? This is clear? Anyone has doubts on why this is Gm and this is Rs parallel 1 by Gm? I'm assuming everyone is fine with this. Great. Okay, so now if I include the effect of R naught, how will this change? Yeah, why? Yeah, so what he's saying is if you include the effect of R naught, I mean for short circuit GM nothing changes. I'm going to short circuit this. R naught will be connected between two grounds, no change. Now when you try to find the output resistance, R naught is connected like this. So it is as though it is connected between the output and ground. So I can redraw it like this. So it is as though instead of RS, I have RS in parallel with R naught. Is this okay?
So will there be a parallel to 1 by GM term?
Yeah, of course. I mean RS parallel R naught parallel 1 by GM, right? So what I was saying is in this expression, wherever you see RS, you replace with RS parallel with R naught. Okay, so let be there. Okay, so here another point I just wanted to maybe make in passing. If I tend GM to infinity, what does it approach? 1. Why? I mean it approaches to 1, but why do you think that makes sense? See, anytime you derive into something, right, first do some sanity checks. So here let's say I derive something. One quick sanity check is to see if the dimensions and the units are correct. What should be the units of gain? Unitless, voltage by voltage. Is the dimension correct? Fine. Next is to take some limiting cases, right? So for some value of RS, do you know what is the gain here? If the RS is infinity, what should have been the gain? 1. That was the case with an ideal current source. If I tend RS to infinity, what do you get? So at least some sanity checks are passed. Now you try to make more sense of it. Now I see that if I tend GM to infinity, it's 1. At least the earlier case when RS tending to infinity, we knew it was 1 because we already understood it. Now why do you think this makes sense?
Because VGS essentially becomes 0. So
yeah, why?
Because of infinite GM, there is
Okay, so let's elaborate on that bit. So let me remove R naught. So here, do you think Vout is going to be finite or infinite? Finite. Which means what can you say about the small signal drain current ID? Will that be finite or infinite? And how is the drain current related to the gate to source voltage? GM times VGS. What is VGS? Vi minus? Now I know for a fact that this fellow is finite, whereas this we are tending to infinity. At least for mathematical consistency, what should this tend to? It's not a strict mathematical derivation, but at least I will say if this is finite, but this is very large, this should be very small. Just the limiting cases. Again, this is basically the same as your virtual ground you would have seen in op amps. Everything is an extension of asymptotic equality. So here, if I have an op amp, if this is Vout, it has a gain A. Again the same thing, Vout is A times Va minus Vout. So once again you do the same thing. If A tends to infinity, if Vout is finite, then this term must be 0. That's essentially a virtual ground principle, and that's why you say that just be. And in this entire argument, there is one important assumption made, which is the fact that this term is finite, okay, and that you can guarantee only if you have negative feedback. Okay. For example, in the op amp case, I can change the signs here to this, right? And the only thing that will change in the expression is this becomes minus A times this. So here I can't make a case that, hey, my A is tending to infinity, so this should tend to 0. It doesn't work that way, because the moment you flip the signs, the op amp is in positive feedback. You cannot guarantee that Vout will be finite. Okay. So only if it is in negative feedback, you can say that the output can be finite. And under that condition, you can invoke this idea. Is that clear? Okay, right? Great. So that's okay. That's enough with common drain. So what all we did? Yeah, gate drain, gate source. Sorry. this is done. Last is input source, output drain. So that is the common gate. That's simple. Let's quickly do it. So gate is common. I apply a small signal Vi at the source. This is Rd. This is Vout. Again, let's ignore R0 to avoid confusions. So what do you think is the small signal Vout here? What is the small signal Vout? Okay, let's do it. MOSFET is a current source. What is the value of the current source? GM? VG? Yeah. So what is that? VGS. Minus GM times? So I don't like minus. Let's all be positive. So let's flip it around and say it's GMVI. So what is the current flowing here? GM times VI. It is flowing to a resistance RD. So what is Vout? GM RD times V. Again, you can also find it using short circuit GM and Rout. You will get the same. But an important use of this circuit is here. So let us say I do the same thing, but the input is say a current source In, and I am interested in this current I out. Again, R0 is ignored, let us say. What can you say about I out and I in? Both are same, right? Now with respect to currents, I see that the gain is 1. So what is the point of the circuit? It is it's a current buffer. What kind of controlled source is a current buffer? Current control. It is sensing some current and buffering it as a current source. It's a current controlled current source. So once again, the requirement of a current buffer is because of this. I'm sure you know it. Let me just mention it for completeness. You have I in, let us say. It can have its own output resistance. If you wanted to connect it to a load RL, if you connect it directly, only a fraction of this current will get delivered to the load. So instead what you do is this, you take the help of a current buffer. What should be the input resistance of an ideal current buffer? 0. Remember, this current buffer has to sense the entire current. So whatever you are putting here must be able to draw the entire current I in. So which means ideally this should be a short circuit, 0 input resistance, so entire current flows, and then you have this guy mirroring it too. Okay. And we can quickly verify what is the input resistance here. Yeah, 1 by GM, we already knew it. Again, it is 1 by GM because I have ignored R0. Okay. Otherwise with RD we cannot exactly say, depends. Great. So that's about the 3 configurations. I'm sure you know it. Let's move on. Anything to be, something not clear, or should I repeat something? Hopefully this should be a recap. Now let's quickly ramp up. Okay. Now remember, our goal is to make an op amp with a large gain, right? Yes. Right.
Any two-terminal device should act like a current buffer. The current which you are going to put in is obviously going to come out.
Good question. So he's saying, yeah, that's a very good point. He's saying anytime I have something like this, I in will be equal to I out. So what is the thing of a current buffer? How does it differentiate, let us say, a simple thing like this from an actual current buffer? Yeah, the idea is it should have a very small input resistance, right? For example, here I do not know what will be the if it has a out here. Now you cannot say that this is equal to this, right? The idea is you steal the entire current from this, and then you have another guy copying the current. The different.
Short circuit wire acts like a current buffer.
But the idea is once you short circuit it, but then how do you copy the current? It is not just about presenting a 0 impedance, right? This is fine, but this current has to be copied here, right? This entire thing is your current control current source. Got it, right? Okay, great. So yeah, now we want to make an op-amp with a large gain. So which of the three configurations is useful? Common source, common gate, or common drain? Common source. So let's say do this V1. So here the gain will be, this is going to amplify only V1, but I want to take the difference between V1 and V2. What is one simple change I can make here so that the current here is dependent on both V1 and V2? If I connect V2 here, the current is GM VGS, GM times V1 minus V2, and we get it. But why don't we do this? Yeah, ideally you want the input impedance for both V1 and V2 to be large. Here, what is the input impedance seen by V2? Okay, let's ignore R0 so that no confusion. It is 1 by GM if we ignore R0. Okay. So the resistance here is small. So what do you suggest? So what is the fix for this? Sure, you have seen this, right? Yeah, you try to buffer it and feed it so that the resistance seen is large. So the idea is this is a buffer of gain 1, this is V2. So then this voltage is V2. The small signal current is what? GM times V1 minus V2. So if this is RD, what is the output? Vout. This is all small signal, okay? Yeah, minus GM times RD. All they have drawn VDD for small signals, it is short. I am just looking at small signals. Okay, it's not exactly correct the way I have drawn it, but for simplicity, I will not show any biasing. We are only looking at small signal behavior. Great. So now, how do you make a voltage buffer? Common drain. So that's what you do. You take V1 and V2 is buffered like this. Okay. Now of course you can have a resistor here also so that it's symmetric, and that gives rise to the proverbial beast, the differential amplifier. So let me redraw it in a different, in a neater way. This is V1, V2, RD and RD. Now I can tap the output from any of the two arms. So let us say I tap it from this and call it Vout. Okay. Cool. So now here when I had an ideal buffer, I knew that the source voltage is exactly V2. But do you think this is an ideal buffer or a non-ideal buffer? Yeah, what is the non-ideality in this buffer? Let's say I have an ideal current source. In this circuit, do you think this is ideal or non-ideal? That basically takes me back to the common drain we saw. Yeah, this guy is ideal voltage buffer or a non-ideal voltage buffer? Okay, what should be the characteristics of an ideal voltage buffer? Infinite input impedance, zero output impedance, and the gain should be close to 1. The gain is 1 here. Vi follows Vout because I have ignored R0 and we have a current source. What is the input impedance? Infinite, looking into the gate. What is the output impedance? 1 by GM. Again I have ignored R0, so looking into source 1 by GM. So is it 0? No, right? So which means this is not an ideal voltage buffer. So which means this voltage will not be equal to V2, right? So that's what you need to calculate. So if I call it Vx, right? So what I'll do is I'll give it as an exercise. Please calculate what is Vx, okay? And we'll continue from this point the next class. Okay, so I'll stop here.